You hear about a comet appearing in the morning sky and the internet explodes. Green glow, interstellar visitor, third of its kind. Everyone scrambles for telescopes, but strip away the breathless headlines and what remains is a fast cold rock that came from somewhere else and will leave forever. No drama, no conspiracy, just physics and chemistry written in ice that survived 7 billion years. So, what is 3I Atlas actually doing in late November 2025? Why does it matter? And what did we learn that changes how we think about comets from other stars? This one was not heading our way. It was 670 million kilometers from the Sun when discovered, just inside Jupiter's orbit, moving at 221,000 kilometers per hour. The designation 3 tells you everything. The 3 means third confirmed interstellar object. The I means interstellar. Before this, we had 1I Oumuamua in October 2017. An asteroid shaped like a cigar or a pancake, depending on who you ask. Then 2I Borisov in August 2019. A comet that looked like our comets, but came from somewhere else. 3I Atlas is number 3. Hyperbolic excess velocity of 58 kilometers per second. That is the speed it had when it entered the solar system relative to the Sun. Faster than Oumuamua at 26 kilometers per second, faster than Borisov at 32. 3I Atlas is moving with purpose. Its trajectory when traced backward points to interstellar space. No Oort cloud, no Kuiper belt. This thing came from a star we cannot name light years away, and it will never return. Also, this script is researched and factual using sources from the monthly notices of the Royal Astronomical Society. Letters published by Oxford Academic in June 2025, specifically the discovery paper by Bolin and collaborators detailing initial observations and orbital calculations, and the Astrophysical Journal Letters accepted manuscript from August 2025 by Cordner and team at NASA Goddard describing James Webb Space Telescope spectroscopy results. These are peer-reviewed primary sources from the institutions doing the actual observations. Now back to the information. Within hours, the Minor Planet Center received the report. Follow-up observations started immediately. Zwicky Transient Facility in California had pre-discovery images from June 14th to 21st. Nobody noticed it then because it was too faint, and the automated detection algorithms missed it against the crowded background. Atlas itself had captured it going back to June 5th. By July 2nd, the International Astronomical Union announced this was interstellar. 122 observations from 31 observatories confirmed it. Eccentricity locked at 6.144. Hyperbolic excess velocity, 57.95 kilometers per second. No debate. This came from outside. Marginal tail elongation 3 arc seconds long. This was not a rock. This was a comet. Gas and dust escaping as sunlight warmed the ice. The comet designation C/2025 N1 got added to 3I/Atlas. By early July, it was clear this would be bright enough to study. Predictions put it around magnitude 10 at perihelion, observable with backyard telescopes. A chance to see an interstellar visitor without needing Hubble. The problem is, you cannot separate the light from the nucleus from the light of the coma. Everything blurs together. What we know is, the nucleus is icy. It has a coma. It is active. Therefore, it is a comet, not an asteroid. But that is just the visible dust and gas. NASA's SphereX mission detected a carbon dioxide coma in mid-August, spanning at least 348,000 kilometers in radius, only visible in near-infrared. The comet was outgassing hard, even at 3.3 astronomical units from the Sun. 3. Atlas flipped the script. James Webb Space Telescope observed it on August 6, 2025, using the near-infrared spectrograph. Results announced August 25th. The coma was dominated by carbon dioxide. Carbon dioxide to water ratio of 7.6 to 1, among the highest ever measured in any comet. Most comets have ratios below 1. A few outliers like C/2016 R2 hit 4 or 5. 3I Atlas hit 7.6. The spectrum also showed water ice, carbon monoxide, carbonyl sulfide, and dust, but carbon dioxide ruled. Second, it might have formed near the carbon dioxide ice line in its protoplanetary disk. That is the distance from a young star where temperatures drop low enough for carbon dioxide to freeze solid. Different from the water ice line, if 3I Atlas formed right at that boundary, it would naturally be carbon dioxide rich. That tells you the stellar environment where it formed had comparable carbon chemistry to our Sun's nebula. Same building blocks, different proportions. The water loss rate measured 40 kilograms per second when the comet was nearly 3 times farther from the Sun than Earth. That distance most solar system comets are quiet. Ice does not sublimate much that far out. 3I Atlas was different. The Swift team concluded sunlight was heating small icy grains ejected from the nucleus. Those grains were vaporizing in space, feeding the coma, not direct sublimation from the surface. Carbon dioxide and carbon monoxide outgassing from the nucleus kicked dust and ice grains into the coma. Then solar radiation hit those grains and turned them to vapor. 40 kilograms per second is not huge, but it is active for that distance. Production rate of 1.5 times 10 to the 25th molecules per second. A week later, on September 14th, the rate climbed to 4.5 times 10 to the 25th molecules per second, 2 kilograms per second. The cyanide coma on September 15th was 180,000 kilometers across and asymmetric, elongated away from the sun. A visible dust tail stretched 50 arc seconds corresponding to 100,000 kilometers. Solar conjunction on October 21st, 2025. Perihelion on October 29th at 1.35 astronomical units, 126 million miles, just inside Mars orbit. Earth-based telescopes could not see it during perihelion. The sun's glare blocked everything, but spacecraft could. ESA's ExoMars Trace Gas Orbiter caught it from Mars. Between October 1st and 7th, the orbiter imaged the comet from about 10 times closer than Earth-based telescopes. The images refined the trajectory. Uncertainty in position dropped by a factor of 10. The Cassis camera on the orbiter was designed to photograph the Martian surface in high resolution. Pointing it at a fast-moving comet required recalculating everything. Flight dynamics teams worked with instrument teams to account for the spacecraft's orbit around Mars. The result was the most accurate trajectory data yet. The Punch mission caught the tail as a short elongation. The Parker Solar Probe, Lucy spacecraft, Psyche spacecraft, and Europa Clipper all turned instruments toward it. The Stereo mission observed it from September 11th to October 2nd using stacked images. SOHO grabbed a glimpse. Even the GOES 19 weather satellite tracked it from October 18th to 24th, when it was faint at magnitude 12. Perihelion happened October 29th. Speed maxed at 246,000 kilometers per hour, 153,000 miles per hour. Pulled by the sun's gravity, then released as it swung back out. The heat should have kicked activity into high gear, more outgassing, brighter coma, longer tail. But we could not see it from Earth. The sun was in the way. Visible again before sunrise, low in the east. It reappeared around November 3rd, 2025, rising about 2 hours before the sun. Predictions put it around magnitude 10 to 11. Faint but reachable with telescopes. The constellation Virgo, near the bright star Spica. Venus shining below as a reference. Clear skies and a low eastern horizon required. The tail was back. Other observers confirmed sightings by mid-November. On November 16th, an observer in Kendal, Cumbria, UK captured it using a C-STAR S 50 smart telescope from the center of light-polluted city. Magnitude around 9.8 based on observations from November 17th. Coma 3 arc minutes across. Tail half a degree long, blue-green color from ionized gases, short spike like dust tail below the coma. The ion tail streaming away from the sun, driven by solar wind. The dust tail lagging behind, pushed by radiation pressure. As the comet rotates, different parts of the surface heat up and vent gas. The plume shifts. Very large telescope images from July and August showed the coma shape changing over time. By late August, an anti-solar tail had developed pointing away from the sun. Post-perihelion recovery showed the tail had grown. The comet remained active, moving away from the sun as predicted. Position on November 24th, 2025, placed it in Virgo southeast of Gamma Virginis, moving northwest. Magnitude estimates around 10 to 11. Some sources reported it brighter, around 9.8, but that depends on observation conditions and methods. Distance from Earth, approximately 270 million kilometers, over twice as far as Mars at opposition, not visible without optical aid. Binoculars showed a fuzzy blob. Small telescopes with tracking revealed the coma and hint of tail. Long exposure photography captured details. The comet moved steadily northwest through Virgo, into Leo through late November and December. If you observed mornings until early December, then switched to evenings, you got moonless dark skies for weeks with only brief lunar interference. Best time to photograph faint objects. Southern hemisphere observers had worse geometry, lower in the sky, shorter observation windows. Northern observers had the advantage. 3. Atlas stayed intact. The gradual fade expected as it moved away from the sun matched observations. Magnitude 11 to 12 through late November, magnitude 13 by end of December, below binocular threshold, telescope only. Still very far. No threat, no close pass, just geometry. After that it headed out, speed decreasing as the sun's gravity pulled back, but not enough to capture it. Hyperbolic orbit means escape. By late December it would be dimming past magnitude 13. By early 2026, it would be too faint for amateur equipment. Professional observatories might track it longer, but eventually it would fade below detection limits, then gone. Back into interstellar space, never to return. 3. I-Atlas gave the richest dataset yet. Carbon dioxide dominated coma. High CO2 to H2O ratio. Water ice grains sublimating beyond the nucleus. Hydrogen cyanide detected. Nickel present, iron absent. Carbonyl sulfide tentatively detected. The carbon dioxide production area calculated at 3.1 square kilometers, enough to drive observed dust release even with large 100 micrometer dust grains. The discovery process itself reveals how detection systems evolved. Atlas Unit 04 at El Sos site, managed by Obstec and Rio Hurtado, operates autonomously. 4 telescopes total in the network. Hawaii, Chile, South Africa. 1 more location. Each telescope surveys entire visible sky every 2 nights. Algorithm flags moving objects. Brightness threshold triggers alerts. 3. I-Atlas moved fast enough and bright enough on July 1st to trigger detection, but archives showed it had been there weeks earlier. April images contained it, too faint to trigger automated discovery. Only after orbit calculated could observers go back and find pre-discovery detections. Zwicky Transient Facility added 28 observations from June. Atlas added observations from June 5th forward. Each observation refined orbit. Each measurement reduced uncertainty. By July 4th, with 319 observations from 97 facilities, the orbit was solid. Eccentricity, 6.144 plus or minus 0.016. Perihelion distance, 1.351 astronomical units. Inclination, 142.9 degrees. Retrograde orbit, coming in from below solar system plane, swinging up through, heading back out above. The inclination explains Mars orbiter views, geometry aligned. ExoMars got clear shots in October. Extrapolation suggests dozens per year, maybe hundreds. Small icy bodies from other stars, most never catalogued. Statistics say at least 1 3 I-Atlas size or larger every 5 to 10 years in inner solar system. But smaller objects vastly outnumber large ones. Power law distribution. For every kilometer-sized interstellar comet, there might be millions of meter-sized ones. Detection bias means we catch the rare big bright ones. The small dark ones stay invisible. Rubin Observatory will push limits, magnitude 24 possible. That reaches smaller objects. Population statistics improve. We learn how many interstellar rocks and ice balls pass through. We learn size distribution. We learn if our system is typical or unusual in receiving this traffic. Water production rate from hydroxyl detection, dust flux from imaging, energy balance equations constrain surface properties. Albedo estimates place it around 4%, typical for comets. Dark surface, organic residue coating ice, the nucleus likely irregular shape. Rotation creates brightness variations. Surface features could include active regions where jets vent, smooth areas where dust settled, rough zones where ice sublimates unevenly. No resolved images exist, distance too great, angular size too small. Even Hubble could not resolve nucleus from coma. All we see is integrated light, models fill gaps, assumptions tested against observations. Internal structure unknown, could be monolithic ice block, could be rubble pile of smaller chunks, could be layered like onion, could be porous like sponge, density unknown, mass unknown. Only size range estimated from brightness and assumptions about reflectivity. But 3i Atlas showed sunward enhancement. Possible explanation involves rotation, axis, orientation. If nucleus spins with axis, tilted specific way, morning side heats up while evening side cools. Morning side vents toward sun. Geometry makes it look sunward when really it is sunrise terminator jetting. Another possibility involves subsurface ice layers. Heat conducts slowly through dust mantle. Time lag means peak outgassing occurs hours after peak heating. Rotation carries that region sunward, appears as forward jet. Without detailed rotation period and axis measurements, speculation only. Observations confirm sunward plume, cause requires more data. Dust tail different, dust particles pushed by radiation pressure. Heavier particles lag, curved tail forms. 3i Atlas showed both. Ion tail straight narrow blue, dust tail broad curved white. Post-perihelion recovery in November confirmed both tails still present. Activity continued, distance from sun increasing, temperature decreasing, but carbon dioxide and water still sublimating. Thermal inertia in nucleus. Heat stored during perihelion slowly conducted outward. Delayed response keeps activity going weeks after peak heating. Standard comet behavior. 3i Atlas followed script. Dust contained organic compounds. 3i Atlas showed blue-green from ionized gases. Less dust, proportionally. Larger dust grains. Different formation history implied. Borisov perihelion, distance 2 astronomical units. 3I Atlas, 1.35. Closer pass for 3I Atlas. Higher heating. Yet carbon dioxide stayed dominant. Volatility suggests deep reservoir, not just surface frosting. Bulk composition enriched. Formation environment must have favored carbon dioxide over water, either temperature or radiation, or both. 4-3I Atlas. U equals negative 51 kilometers per second. Moving outward from center. V component places it rotating with galaxy, but details uncertain. W equals positive 18.5 kilometers per second. Moving upward out of plane. High W velocity rare. Most stars and objects orbit in thin disk, low W values. Thick disk objects have higher W. Older population, lower metallicity. Formed earlier in galaxy history when disk was thicker and less settled. 3I Atlas kinematics consistent with thick disk origin, but thin disk not excluded. Observational uncertainties allow both interpretations. More precise velocity measurements needed. Maybe Webb can detect spectral shifts from gases. Maybe ground-based, high-resolution spectroscopy can measure Doppler. Velocities refined over time as more data accumulates. Age estimates put 3I Atlas between 7.6 and 14 billion years old, based on galactic kinematics. The velocity components traced backward through the Milky Way. U velocity negative 51 kilometers per second away from galactic center. W velocity positive 18.5 kilometers per second upward through the galactic plane. High W velocity suggests thick disk population. Thick disk stars are older. Lower metallicity. Formed during cosmic noon epoch 9 to 13 billion years ago when star formation peaked. If 3I Atlas came from a thick disk system, it might be twice as old as Earth, a relic from the early galaxy. The interstellar velocity signature retained since ejection. Tension and population assignment remains. More data needed. Either way, it is old. Different distances from parent stars, different radiation fields, different disk chemistries. The sample size is 3, too small to generalize, but the differences are real. Estimates suggest at least one 3I Atlas-sized object every 5 to 10 years. Many smaller ones likely pass undetected. The Vera Rubin Observatory coming online will find more. Wide field, deep imaging, rapid cadence, designed to catch transients, interstellar visitors included. It climbed higher in pre-dawn sky through November and early December. Magnitude 10 to 12 made it accessible to serious amateurs. Not naked eye, not easy binocular target, but reachable with 6-inch to 8-inch aperture telescopes under dark skies. Astrophotography rigs with tracking and stacking pulled out details invisible visually. The blue-green coma, the ion tail, the faint dust structures. 3. I Atlas is a comet from another star. It carries ice formed billions of years ago in a disk around a sun we cannot see. Cosmic rays and starlight battered it for eons. It wandered the galaxy until gravity slung it toward our system. We had months to study it. Hubble, Webb, Swift, ground telescopes worldwide, Mars orbiters, spacecraft across the solar system. Spectroscopy revealed chemistry, imaging revealed structure. Astrometry refined trajectory. The data fills archives, papers published, more coming. By century end, light years away, heading wherever its trajectory takes it. Maybe another star system someday. Maybe another civilization with telescopes watching it pass. We were the ones who saw it this time. High ratio compared to water suggests formation conditions or evolutionary history, unlike typical solar system comets. The detection of water ice grains sublimating in the coma instead of just at the nucleus shows complex activity mechanisms. The lack of iron with presence of nickel raises questions about metal chemistry. The age estimates place it among cosmic noon-era relics. The trajectory data refined by Mars observations improved ephemeris accuracy for future interstellar object intercepts. Southeast of Gamma Virginis, the comet moves northwest daily. Use Venus as anchor, Spica nearby. Magnitude 10 to 11 requires dark, adapted eyes and patience. Averted vision helps, look slightly to side of suspected position. Peripheral vision detects faint fuzz better. Photography requires tracked long exposures, 30 seconds to several minutes. Stack multiple frames. Process to enhance contrast. The coma appears first. Tail emerges with more exposure time. By Christmas 2025, Earth will be in its rear view mirror. The comet heads back to interstellar space. The gap widens. Light travel time increases. The brightness drops. Magnitude 13, 14, 15. Professional telescopes might track longer. Adaptive optics, large apertures. But eventually even they lose it. The signal fades below noise. The comet vanishes. The observations end. The data remains. Physical legacy. Research laboratory in India observed it mid-November from the 1.2 meter infrared telescope on Mount Abu. Spectroscopy in near infrared, more composition data, more confirmation of CO2 dominance. European observatories contributed astrometry. American facilities added photometry. Japanese telescopes joined. Australian, South African, Chilean, collaborative global effort. Everyone wanted a piece. Interstellar visitors do not come often. Space is empty. Trajectories blur over billions of years. Peak activity might come days or weeks after perihelion. Observations in November captured that delayed response. The coma is still active. The tail still present. The comet still outgassing as it cooled. Hubble caught 4 glowing fragments. 3I Atlas stayed intact. No splitting, no sudden brightness surges from fresh ice exposure. Stable structure. Whatever holds it together survived perihelion. Separating nucleus rotation from coma changes requires sustained monitoring. Few facilities committed enough time. The data exists, but analysis ongoing. The ion tail fluoresced in ultraviolet. Standard comet behavior. The only unusual part was origin. Triangulation from multiple observatories. Spacecraft at different locations. Refine orbit. Predict impact or miss. 3I Atlas posed no threat, but the exercise refined methods. Interceptor not ready. Next time, maybe. If another interstellar comet arrives before 2030 and trajectory allows, Interceptor could attempt rendezvous. One-shot mission, no second chances. Pick target carefully. Protoplanetary disks vary. Distance from star matters. Stellar luminosity matters. Disk mass and density matter. Every system has slightly different chemistry. The planets and comets that form reflect that. 3I Atlas shows us one example. Borisov showed another. Oumuamua maybe a third if it was icy. More samples needed. Each interstellar visitor adds data point. Slowly the picture fills in. The late November viewing window closes by mid-December. Moon returns. Dawn sky brightens. The comet dims. By December 19th, closest approach passes. After that, recession accelerates. Magnitude drops faster. By January 2026, it likely below magnitude 14. By March, below 15. Amateur equipment cannot reach it. Small professional telescopes struggle. Large observatories with sensitive cameras might hold it longer. Hubble could track into spring 2026 if telescope time allocated. Webb could detect it even fainter if justified. But priorities shift. New targets appear. Interstellar visitor fades from spotlight. Archives hold the data. Papers in review. Analysis continues. The observations speak. The comet itself will be light years away, but the data permanent. That is the value. We got months of multi-wavelength observations from discovery in July through fading in December, ultraviolet from Swift and Hubble, visible from ground telescopes worldwide, near-infrared from Webb and SphereX, mid-infrared from ground facilities, sub-millimeter from James Clerk Maxwell, radio silence, radar impossible at that distance. But optical and infrared coverage dense, photometry, spectroscopy, imaging, astrometry, polarimetry. Every technique applied, the dataset robust. The third interstellar object gave the richest science return yet. ZTF scanning, Rubin soon scanning, automated alerts, follow-up networks, space telescope trigger programs. Next time reaction faster, observations deeper, understanding sharper. No conspiracy. No aliens, despite one researcher floating the idea. Just a comet from another star, composed of ice and dust, billions of years old, traveling fast, visible briefly, studied intensely, now leaving, forever. That smudge traveled 7 billion years or more to be in your field of view for that moment. The photons hitting your eye or camera left the comet 8.5 minutes ago, traveling at light speed. Before that, they bounced off ice grains in the coma. Before that, they left the sun. Before that, the ice formed in a disk around a star long dead or still burning somewhere in the galactic disk. The atoms in that ice witnessed the Milky Way before Earth existed. They survived supernovae shockwaves. They drifted through molecular clouds. They got ejected from a planetary system in formation. They wandered. They found our sun. They warmed. They glowed. You saw them. Radiation pressure, chemical bonds, sublimation, ionization, dust scattering, all the processes that govern comets everywhere. The only difference is birthplace. This one was not born here. It came. It showed itself. It taught us. Now it goes. The reality delivered rare data, composition measurements, activity profiles, trajectory refinement, age constraints, chemistry clues, formation environment hints, the observations documented, the papers published. The comet moves on, the knowledge remains. We learned interstellar comets vary in composition more than expected. We learned carbon dioxide can dominate in ways rarely seen in solar system comets. We learned multi-wavelength follow-up campaigns work. We learned Mars orbiters can refine trajectories. We learned SWIFT can detect water vapor from faint, distant comets. We learned Webb can measure isotope ratios. We learned ground telescopes coordinated globally can track a magnitude 10 object through dense star fields. We learned. Maybe never. The galaxy is big, the odds are low, but the trajectory continues. The comet endures, the ice remains frozen in darkness, the carbon dioxide, the water, the carbon monoxide, the dust, the metals, all locked in ancient ice waiting for the next star to warm them again. That is the story. That is the late November morning sky return explained without the hype. An interstellar comet, faint, fast, fascinating. Observed, understood, gone.